Welcome to Brain Vision.
Okay, for this question, we're going to use Debye's t-cubed law to solve some problems. So Debye's law is given by this equation here that's boxed. The specific molar heat capacity is equal to K, which is a constant, times temperature cubed over theta cubed, which is another constant. So for part A, we want to find how much heat is required to raise the temperature of 1.5 moles of rock salt from 10 Kelvin to 40 Kelvin. So in the problem, it gives you a hint to use dq equals nc dt. So for this, we're going to use some calculus. So if we want to find the total amount of heat given a temperature range, what we're going to do is take the integral of this dq expression, because we already have our interval of temperatures from 10 Kelvin to 40 Kelvin. So we can integrate this differential equation to get our total heat. So here we go. So to integrate, we're going to say Q will be equal to integral from T1 to T2 of this expression, NC dt. Okay, give you some more room here. Perfect. So the thing is, since we're using Debye's t-cubed law, C is in terms of T. So we have to plug in this equation that we have for C into this integral expression. So we can go ahead and write. So N is the variable known for the number of moles, which will be 1.5, but for now we're just going to leave it as N. Since it has nothing to do with T, we'll bring it out of the integral. It's from 10 to 40 Kelvin. We know C is K T cubed over theta cubed dt. So that's just a number that will come out. That's just a number that will come out of the integral. So really our integral is pretty straightforward. It becomes nk over theta cubed. Then the actual integral, which we're going to solve here pretty easily, 10 to 40, our temperature range of Kelvin, and then T cubed dt. So yeah, all we have to do now is solve this integral. Then we'll have our answer. Q is equal to, go ahead and solve it out for you guys here. So we have our constants out front here, nk over theta cubed. And then integral of t cubed is just t to the fourth over 4. So t to the fourth over 4. Let's write a better 4 than that. T to the 4 over 4 evaluated from 10 to 40. Now if you plug in n, which is 1.5, k, which is 1,940, and sigma, I'm sorry, not sigma, theta is 281, you can solve this out here and you'll get that Q, or the total amount of heat required to raise 1.5 moles of rock salt to raise the temperature from 10 Kelvin to 40 Kelvin, is 83.61 joules. But since we want to heat this object up, we'll be taking heat from the environment, so there should be a negative attached to that number. Okay, moving on to part B. So part B is very similar in terms of we'll be using some calculus to solve for the average molar heat capacity in the same temperature range. So we've already kind of done this, but we're going to think of it as finding an average value for this molar heat capacity from 10 Kelvin to 40 Kelvin. So we know that C, which is the molar heat capacity, is equal to this. This is Debye's law here. T cubed over theta cubed. So we want to find the average of this over a certain range, all we're going to do is integrate again. Pretty self-explanatory here. So we want to get, by this certain range of values, we're going to get an average value of C from that temperature range. So it's going to look something like this. Let me just write it out. So to get this average C average, it's going to be equal to this integral. Again, it's 10 to 40. That's our temperature range. Okay. And we still have K T cubed over theta cubed. But the thing is, we're looking for an average value. So just giving this integral isn't going to do it. So we know from earlier math to take an average of something, you add everything up over the interval and divide by that interval. So that's what we're going to do. So we have this integral, then we have to divide by 30 because we're doing from 10 Kelvin to 40 Kelvin, so that the distance of the interval, or the difference between those two points, is 30. Okay, so going down here again, giving myself some more room. We now have C average is equal to, let's write that better. C average is equal to 1 over 30, which is how we get our average value of a function from calculus class. 1 over 30 times K over theta cubed. And again, we're going to integrate this T cubed again, just like in the previous part. Okay. T cubed, and of course, don't forget their DTs. DT, DT. So again, this T cubed integrates the T to the 4th over 4. Then we're just going to evaluate. So evaluate that out. Again, this will be K over 30 times, see if I can draw a good theta. That's okay. Theta cubed times T to the 4 over 4 from 10 to 40. And then we get our answer after you evaluate that out, to get that your average molar heat capacity is 1.86 or 1.87. There's going to be some round off based on how exact you are with your values. But again, is this positive or negative? So in the part A, we realize that since we're drawing heat from the environment, from the greater system to heat our rock salt, that heat is really negative because you're pulling from the greater environment. So this means this answer has to be negative also to match up with our signs to keep it consistent. Like the signs, they're important, yes, but it's more important to understand how you define the system, and then make sure that how you define it stays consistent with the whole problem that you're doing. Okay, and then part C, this is just a plug and chug equation. So we want to find the true molar heat capacity at 40 Kelvin. So we're just going to use Debye's law straight up and plug in 40 Kelvin, and that'll be our answer. Okay, it's 40 Kelvin cubed over, again, it's just theta. Again, K and theta are given, so this is really just a calculator problem after you've done the hard work in A and B. And this comes out to be C at 40 Kelvin is 5.596. Again, there'll be round off based on what your homework set wants to be. And there's our answer.